Hello. Today we are thinking about molecular compounds. So now we're going to start by thinking about the covalent bond instead of the ionic bond. So we remember that ionic bonds were when you had one element that was losing an electron and the other is gaining. So if this is your valence electron, if I've got a metal atom over here and I've got a nonmetal atom over here, then the nonmetal is going to gain the electron, the metal loses it, and so we have a cation and an anion. These are attracted because of opposite charge now. And that's one type of attraction. That's an ionic bond. And remember, the big deal is that the positive ion didn't really care about which negative ion it attracted to. It attracted to every single one and made these giant crystals, and that was an ionic bond. In a covalent bond, what's going to happen is you have two atoms that both are electronegative. They're both trying to gain. And so this atom is trying to grab the electron from here, and this one is trying to grab the electron from here. So you have what ends up is they kind of both are, give me yours, no, give me yours. No, it ends up kind of being a fight over it, that this electron is trying to be grabbed from over here, and this one's trying to grab from over there. So they end up kind of fighting over both of them. It's not, nobody's giving up. Nobody's letting go. They're both trying to gain both of them. And that's what we actually mean by sharing, which if you have siblings, sometimes you know that sharing looks a little bit more like fighting than sharing, right? We have to actually take our turns in real life. Yeah, but so what we're talking about is, again, they have similar electronegativities. They're both trying to gain electrons from each other. And so nonmetals, we said, the ones on the right tend to have higher electronegativities. And so this kind of bond is going to happen because of that. Neither of them has real low electron ionization energies like metals. Neither is going to give up an electron easily. And so we think about this as ionic bonds are where one is stolen, well, one's gaining, it's taking it away, and the other's just like, yeah, whatever, have it. In a covalent bond, since they're both trying to gain, they're both shared, or they're both kind of fought over by both elements. And so we can think about a covalent bond is generally between nonmetals and other nonmetals. It's made up of entirely nonmetals. When you're looking at a compound and you see all nonmetals, that's when we're going to think about it as a covalent one. And what we're going to think about on this is that this is now going to have a specific group of atoms. Instead of a big crystal like an ionic compound, what we're going to talk about is a covalent molecule that is a specific amount of atoms, so that one atom is bonded only to one other one, and that's it, not any other ones around it. And so when we start to make this at a larger scale, it does not form a crystal. In fact, these two molecules, even though they're the same, would not really have a lot to do with each other. And so this can happen between two of the same type of atom. In fact, there are 7 different elements that this is the natural state that this happens in, and those are called diatomic if it's the same type. So 2 hydrogens, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you kind of think of it like the halogens are in a line, and then it kind of makes a little 7. There are 7 elements that do it, and then you just have to remember hydrogen. It's already an exception. So those are always come as pairs. So hydrogen, nitrogen, oxygen, and the halogens, or at least the ones towards the top, except for the bottom, astatine, and not tennessine either. That's the new one, 117. But those are diatomic elements that actually make covalent bonded molecules with themselves. They're so reactive that they react with themselves and make a pair and share those electrons. We can think about these molecules as opposed to the ionic crystal where it bonded with everything, every negative bonded to every positive it could to make a crystal. These are more individual molecules. This is like a ball in a bucket. You could grab this ball out of here. And so the Legos are more like the crystal that they build up and build a really strong structure where the balls are kind of separate from each other. And so some properties that go along with that is we would expect them to have lower melting and boiling points because melting is when these can move around each other. And they can do that as opposed to the crystal where there's a lot of bonds to break in order for that to happen. Boiling point also, boiling would be where it becomes a gas. They oftentimes are a little bit softer where this crystal, the ionic, is going to be really hard to crush if we try and crush it. These ones we try and crush. Sometimes they're a liquid at room temperature already. They don't dissolve as well. Just because of the nature of each of these having a positive or negative charge. Covalent, there's no charges here. Nobody's gaining or losing. They're both sharing those two electrons. And so they don't conduct electricity when they're dissolved. That's again because these are positive and negative ions. When they dissolve, they still maintain that whoever gained, gained, and whoever lost, lost. But this one, there's no charges. So they don't conduct electricity in water. And a lot of times, these covalent ones are made up with carbon or hydrogen or sometimes sulfur. They can burn more. They have this tendency to burn more. And so we see those properties. And so big idea is that while the covalent bond itself is very strong, the attractions between the covalent molecules are much weaker. And so when we talk about a big covalent compound, a whole bunch of molecules, sometimes they're solids, especially if these molecules are bigger. Sometimes they're liquids that they freely move around each other, and sometimes they're gases that they're not even in the same space really, that they're fall all apart. And you can think about that kind of as the covalent is taking a ball out of the bucket kind of thing. You take a ball out of the bucket, you're taking a molecule, separating it from the other molecules, but you're not breaking the covalent bond. We're just separating the molecules from each other. Whereas with ionics, they're in a big crystal, and so we're pulling Lego pieces off. And to really break this down, it's a lot of structure to break apart. So the nice thing is that we can write a molecular formula. This is a little bit different. It looks the same with ionics, but ionics we were writing what we call the formula unit, if you remember that. And that was the lowest ratio in the crystal. A molecular formula is going to tell us exactly how many atoms are bonded together. So in H2O, it's 2 hydrogens and 1 oxygen in every single molecule. It's always 2 hydrogens bonded to 1 oxygen. They're in this exact ratio, and that's called a molecular compound or a molecular formula. Here's another one for ammonia. Ammonia is NH3. That's again 1 N with 3 H's. The little number in the bottom right, that means how many of that atom are bonded together. And when it's covalent, that's exactly how many atoms are in that molecule. So to summarize that, we can think about covalents are molecules where the total exact number inside a single molecule bonded together versus a formula unit, the lowest ratio in the entire crystal. Covalent is going to be nonmetal to nonmetal. Ionic is going to be metal to nonmetal. And so covalent tends to have lower melting and boiling points because they can move around each other. Ionic is higher because we have a lot of bonds to break. When dissolved, covalent do not conduct electricity. When dissolved, ionic do conduct electricity or melted. but not as a solid, not as a solid if you put this on a salt. And then when you think about this, in the bond itself, the electrons are shared. Remember, they're fighting over them. And here they are transferred. One gains, one loses. And so that shared versus transferred causes a lot of different things with the properties of what those are like. Have a great day. See you soon.